Hello everyone, I hope you all are doing well. This side Priya Bhatia, and in this video we will continue our discussion of EDA. And if you remember till so far, we have seen in our last session that how we will be able to detect the outliers. And then we have seen how we can do normalization, why it is important, right? Via standard scalar form. We have seen that how we can do so. I have told you about two techniques. Either you can go for standard scalar or you can go for min max scalar, and the importance is that we need to reduce the biasness, everything we have covered up with the implementation, right? Now in this part of the video we will see that okay, one way we have seen in the last session where we have talked about that, let's say we have a outlier, so how we can remove those outliers. Obviously, it's not good to have a removal of all the outliers available in the data set. But yes, if we can remove, maybe 40-50% out of them, that is a good deal, because remaining outliers will act as a noisy data points which will make your model more robust in future with respect to test data, right? It's like you can relate it to personal life. Let's say if I will say if only good things will come into your life, you will become very weak, right? That bad things will make you more strong in order to deal with the practical scenarios in our real life, right? Similarly, for the model training also, if we will give few bad data points which will basically help my model to make more robust in future, because you never know when you do the deployment part per se, bad points will also come into picture, so my model should know that how can we handle those points. So that's the only idea. So one approach we have seen via calculating the quantiles. If you remember, we have talked about how we will be able to get the lower bound and upper bound. This is simple stats. If you have any confusion, just look into the stats portion of box plot. It will be very easy. Now second approach is the quantile approach. So let me talk about today that what is empirical formula first in statistical analysis, and then maybe you will be able to understand this concept in an appropriate manner. So I hope you can see on my screen this simple plot. It's nothing but it's called as the normal distribution, or it's very famous by the name of Gaussian distribution as well. So this is a kind of a distribution which is, you can say, is a normal distribution, or it is also famous by the name of Gaussian distribution. Now if you will observe this distribution very very keenly, or distribution, right? If you will observe this distribution very keenly, you will be able to observe, first of all, this is nothing but symmetric. So this is also called a symmetric distribution, where what you have observed is experimentally, again, it's been already proven that when your data is among the range of mu minus sigma to mu plus sigma, right? Mu minus sigma to mu plus sigma, in that case almost 68.27% of data lies, right? This is probability density, and this is the range, right? Similarly, from mu minus 2 sigma to mu plus 2 sigma, almost 95% data is there. And similarly, from mu minus 3 sigma to mu plus 3 sigma, almost 99% data is available. So what you have observed is that in this kind of symmetric distribution, this is the specific range of the data points that we have. Now, what we will do is today, we will try to utilize the concept of quantile, and let's see that within 99 percentile of quantile, how much data is there, and maybe it will help us to remove the further outliers available in lot many data points that we have. So here you can see zero. One important thing is here we don't have a column name. That's something which is not great. So maybe what I can do here in this particular part, first of all, let's create a column name. That's important because we don't know what this zero indicates in the box plot, what this one indicate in the box plot. So let's do that thing first. So how can we do that? Maybe we can just first of all check our original data frame dot columns, so that we will get an idea what other columns we have. So I think we have pregnancies until this point of time, right? So I'll copy this and I'll do one thing. I'll create a name as columns where we will be having all these column values, which is pregnancies, glucose, BP, skin thickness, insulin, BMI, and diabetes, pedigree, function, and age. So I believe there are 8 columns: 1, 2, 3, 4, 5, 6, 7, 8. Perfect. 0 to 7. So when we are creating a data frame of x underscore scaled, the only thing which I think we're supposed to do is to define this columns value as scores. Let's see if this makes what we want to achieve here. Let's try to achieve this. Perfect. So what you can see here, now our x underscore scaled is renamed with the proper column names. So now if I just want to achieve the box plot again, which you can see here with respect to this data frame, if I'll just do it again, just why it is showing nan values, let me see it again. X underscore scaled. There is some confusion here. Let me just check it out. X underscore scaled. So it's perfectly fine. Let me try to create a box plot again. This is also fine. Now what we are doing is we have a columns value and we're trying to convert that into a data frame, because if let's say we will check the type of this x underscore scale, let me check it once. It is a ND array. So I want to convert it into a data frame. So I have mentioned p data frame. Let's try to do it again. Now I think it's fine. Let me try to create a box plot again. Maybe what I'll do is I'll try to take the same code and we'll copy it here. Let's try to see this now. Now can you see the same plot is visible, but what I want to achieve is now achievable, because here you can see on the x-axis we have clearly the column names as well, and that is what I want. Right now what I was saying is the problem is still there are so many outliers. I want to reduce quite a more in this particular data set. Obviously, again my target is not to remove 100%, because again there is a somehow loss of information which I don't want. So what I will do is I'll try to reduce it further more a bit. So what I can do, I can use the concept of quantiles now. So the question is how we can do so. Maybe I'll try to take a data which is x underscore scaled, right, of insulin until I would say 95 percentile. So what I'm saying is give me a data point belonging to 95 percentile. So what will happen is, now let me try to show you initially what is the scale or the shape of the data that we have. You will be able to see we have 759 points, because if you remember one work which we have already done to remove the outliers. So in total, if you remember, in the data frame dot shape, our data points are in total, in original data points, it is 768. We have somehow removed it to 759. Let's see now how much removal will happen. So we are storing it in a new data new part. So let's see how will it works. So now we have data new dot shape. Let's see how will it looks like. And you will be able to see that somehow from 759, now the number is again reduced to 721, means there is again a bit of removal of outliers that we have done. So let's see how our new plot looks like in the form of a box plot only. So maybe again I'll copy this code and we'll paste it here. The only difference is, now instead of taking x underscore scale, I'll take data new, and let's see now how our plot will look like. So now you can see that there is a major reduction of outliers. I hope you're observing this particular plot and you can clearly compare this plot with the above one. So what you can do at your end now is you can just check the specific range, maybe at 99% percentile of quantile if you will use. There is more reduction and you will get better quality of data. I'm not doing it here, hit and trial thing, but at your end, maybe definitely you can try. I'll share this code file with everyone. You can try and maybe you can give me the number on which you are getting a better quality of data. And I don't want this to remove this particular number to be also very, very less. Please make sure you don't remove the maximum outliers, because you will get a shortage of data at that point of time, and your training will not happen in an appropriate manner. So we have to take this number in our head that our data removal journey that we are doing here should not be that much less. Maybe let's say in total we will be having 768 data points. So don't come until maybe 400 or 300, because you remember, right, that the more data points you have, better you will be able to train your data. So I think it's a good number that we have 721, and we have even reduced a lot of outliers here. If more than that, maybe if you can jump towards 700 also, it will be appropriately fine, but don't go beyond that, I would suggest. And now I think it's the right time that, so this is the second approach, number 2, I would say, to reduce the outliers. And here we have used the approach of quantiles. Quantiles. We have used the approach of quantiles, right? So this is how this thing will be done. Further moving ahead, let's talk about the next important thing, which is about that how we can train our model, right? This is the next important point which we have to understand. So in upcoming video, we will do the model training part now. We are ready with the data points. Now, the next important part which we have to see is the training part. So what we will do is we will try to apply the logistic regression algorithm on top of this new data points that we have, and we will be able to see how much accuracy we will be able to achieve here. So with this, let's end today's video. I'll see you all very soon in the upcoming video.